Welcome back. So in our previous videos, we had covered how to do hypothesis testing between two independent samples. So if we have sample A and sample B, how do we test whether they have the same means or they are coming from the same underlying population? But suppose we have got three samples that we want to test, and let's assume the samples are A, B, and C. And I want to test whether these three samples are coming from the same underlying population or not. In this case, if I use a two sample t-test, I'll have to test A with B, B with C, and then A with C. So I would have to execute three underlying tests to check whether all three are coming from the same population or not. If I want to do it for three or four or more samples, the number of tests starts to increase rapidly and it becomes pretty cumbersome to do all the comparisons using a t-test. So this is where another kind of test comes very handy, which is the analysis of variance, uh, also known as one way ANOVA or the F test. In this test, we can compare two or more than two samples in one shot or in one procedure itself. The null hypothesis when we are doing this test is that all the samples are coming from the same underlying population. So for example, if I've got, let's say, three samples, and sample 1, sample 2, and sample 3, then the H naught becomes that the samples are coming from the same underlying population of mu1 is equal to mu2 is equal to mu3. Now the alternative hypothesis is supposed to be the exact opposite. So the exact opposite is not that mu1 not equal to mu2 not equal to mu3. The alternative hypothesis is that at least one sample comes from a different population. So this could mean that mu1 is not equal to mu2 is equal to mu3, or mu1 is equal to mu2 is not equal to mu3, or mu1 is equal to mu3 is not equal to mu2. It could be any combination. So the alternative hypothesis does not tell us which particular sample is different, so we'll have to actually break it down into post hoc tests. But the null hypothesis specifies that all samples are same. Alternative would simply specify that at least one sample comes from a different population. Now, while the name of the test is analysis of variance, it is called ANOVA because we are actually testing the variance of the population to derive something regarding the mean. And I'll explain how we are going to look at the variance of the population, then figure out whether the means are same or not. So we're going to go by into the background of ANOVA a little in the next few slides. And we are going to talk about the statistics which lies behind ANOVA for us to better understand how to use ANOVA and what is meant by the term analysis of variance. Now the most important part is, like, for all hypothesis tests that we've checked out till now, this hypothesis test is also based on extension of the central limit theorem. More specifically, it is based on the relationship between sample standard deviation and standard error of the mean. And we know that we can always derive the standard error if we know the sample standard deviation, which is simply the small s divided by under root of n. So if I have the sample standard deviation, I can derive the standard error. If I have multiple samples and they are all coming from the same underlying population, then I can actually start comparing the standard errors from different samples and start inferring the population variance from this. So if I have the standard error of the mean, I can start figuring out what should be the population variance, because we know that the small s over here is replaceable by big S, which is the, say, population variance as well. And how do we actually go about doing it? The F test is nothing but the ratio of between group variability divided by within group variability. And I'm going to ask you to put this into the background a little. What do we mean by this ratio for now? And I'm going to go into these separately. So this is the numerator and this is the denominator of the F test. How do we actually calculate the between group and within group variability? For example, I've got these three samples over here. I've got sample A, I've got sample B, I've got sample C. and we want to test whether the means of sample A is equal to the mean of sample B and sample C, or more specifically whether A, B and C are coming from the same underlying population or not. So what I can actually do is I can calculate what is the between group variance, which is the numerator. I can calculate what is the within group variability, which is the denominator, and look at the ratio between the two. The larger the value of f, more is the probability samples are being extracted from different populations. And why is that? When I look at the between group variability, so let's assume, so I'm going to go into the drawing program and figure out what do we mean by between group variability and within group variability. For example, the central limit theorem tells us that if I have a population and I start extracting multiple samples, so I'll call this the sample column, and I'll call this the mean of the sample column. So I extract sample 1, sample 2, sample 3, and so on. So I have mean 1 for let's say I have sample mean 1, x1, x bar 1, x bar 2, x bar 3, and so on. So I know that the central limit theorem tells me that irrespective of whether the sample is normally distributed or not, or even the population, this variable, which is the sampling distribution or the means of the samples, this will follow a normal distribution, and this normal distribution will have a standard deviation based on this variable. So this standard deviation is known as the standard error. So the distribution of the sampling population is going to have a mean which starts approaching the population mean. So this mean is going to start approaching the population, which is nothing but the mean of this variable, and the variance of this variable is going to be the variance of this distribution itself. So if I have this particular data set, I can calculate the standard error. So if we go back to our example, we've got 3 samples, assuming these are the 3 samples S1, S2, S3, and I have means of these samples x1, x2, x3. So these are nothing but points on this distribution. So if I look at this distribution over here, I would plot these means. I can effectively find out what is the distribution this sampling, what is the mean and the standard deviation of the sampling distribution. So once I do that, I can extract the standard error. So by looking at these 3 different samples and how their sample means are plotted onto this distribution, I can theoretically extract the standard error. And looking at this standard error, I know that standard error is nothing but the standard deviation divided by under root n. So I can theoretically extract what should be the population variance as well. So by looking at the different samples, I can estimate the population variance over here. So we're not estimating the population mean as of now, we are looking at the population variance. So I get a population variance estimate by looking at the means of the different samples and the distribution they follow on the normal curve over here. So this is referred to as the between group variability. Now if I look at the denominator, it means the within group variability. So if I look at this data set again, so not only do I have the means of these different samples, but I've got these different samples as well. So S1 over here is consisting of elements A1, A2, A3, etc., which is nothing but the number of rows. Then I've got sample S2 as well. I've got sample S3 as well. So I've got the observations of all of these samples. So I can assume that this big sample is actually a representation of the population. So if I calculate the variance between all of these samples, so I'm not looking at the within group variance, I'm looking in the variance inside of all of these samples, I can again make an estimate regarding the population variance. So in fact, I have 2 methods of estimating the population variance. One is by looking at the variance within the samples. The other is when I look at the variance inside the samples. So I have 2 estimates. So one is the estimate if I look at the between group variability, and the other is within group variability. Now what will happen if these two, if all the samples are coming from the same underlying population? If they are coming in the same underlying population, then the estimate of the population variance by looking at between group variability is going to be very close to the within group variability. In that case, I will have an F value which starts approaching 1 or even lower than that. But if my samples are coming from very different populations, then these two ratios are going to be very far apart from each other, and I will get F values which are very large. So by looking at the F ratio or the estimate regarding the population variance between these two methods, I can figure out whether the underlying samples are coming from the same population or not. So this is an elegant method of figuring out or testing multiple samples at the one shot by looking at the central limit theorem distributions over here. So to do an illustrated example of how this works, I'm going to look at these three samples. I've got sample A, B, and C. Each of the samples has got 7 observations. So let's make this full screen. So each of these have got 7 observations. So the number of observations in each of the samples need not be the same. So I don't need to have completely balanced samples. So these samples can have various levels of observation. One sample can be 50, the other sample can be 100, the third sample can be 75. It doesn't matter. What we are going to test is whether all these 3 samples are coming from the same mean or not. So the first step is that I need to calculate the between group variance and then estimate the mean group variance. The way to do that is if I look at these 3 samples, sample A, sample B, and sample C. These samples have got means of 7.3, 10.4, and 7.4 respectively. The overall mean, which has to be weighted by the sample size. So we look at the means by weighing each of these samples based on their number of observations. So in this case, we don't need to do that because all 3 samples have exactly the same number of observation, which is 7. So once I look at the means of these 3 samples separately, I also look at the overall mean of all the observations put together, which is 8.04. Now the between group variance is calculated as the sum of squares. So this term is going to be used extensively. Sum of squares between the sample mean and the overall mean. So what I will do is I will look at the mean of A, the mean of B, the mean of C, and figure out how much does the mean of each differ from the overall mean. So this gives us this expression. So 7.3 minus 8.04 whole square plus 10.4 minus 8.04 whole square plus 6.4 minus 8.04 whole square again. And to make sure that we are weighting this based on the number of observations, we multiplied with the number of observations for each of the samples. In this case, all 3 samples have got equal observations, so 7 is multiplied with each of the expressions. In case they are not, we simply multiply each of these expressions with the number of observations. So we get the total between group variance as 62.09 over here. To calculate the mean, I need to divide it by the number of samples that I am using it. And since the number of samples, whenever we are estimating the standard error, we always divide it by s by under root n, where n is equal to the number of observations in the data set minus 1. So we always take a minus 1 to correct it for the degrees of freedom. So in this case, I have 3 observations, which are my 3 sample means. The degrees of freedom in this case I have is 3 minus 1, which is 2. So 1 is subtracted to get the degrees of freedom. I've got 2 degrees of freedom. So my mean between group variance is 31.05. So this is the average between group variance that I have across the 3 samples. So this is my numerator. To calculate the denominator, we calculate the within group sum of squares for each of the samples against each sample mean. So I know that the mean for sample is 7.3. So for each observation, I calculate the sum of squares. That is simply that observation minus the sample mean whole square. For sample B, the mean is 10.4. For sample C, the mean is 7.4. So once I calculate the squared error term or the sum of squares, I can add it up. So I get the total sum of squares as 294. Now, so this is my total within group variance. But I again need to generate the mean within group variance. So I need to divide it by the number of observations. When I'm dividing it for the number of observations, I need to look at the number of degrees of freedom again over here. The way to do that is I subtract the degrees of freedom for each of these samples separately and add it up. For sample A, I've got 7 observations, so degrees of freedom is 7 minus 1, which is equal to 6. I do the same for B, I do the same for C. So total degrees of freedom in this data set is 6 plus 6 plus 6, which is 18 degrees of freedom. So I get 7 minus 1 plus 7 minus 1 plus 7 minus 1, so total 18 degrees of freedom. So I need to divide this number 294.86 by 18. So over here, so I've made a mistake in the PPT. So this is not 340 by 0.86, it's actually 294.86. So I'll fix that. So 294.86 divided by 18, I get the total degrees of freedom as 16.38. Sorry, the total mean within group sum of squares as 16.38. Now the F ratio is nothing but the between group mean sum of squares divided by the within group mean sum of squares, which is 31 divided by 16. So I get a F ratio of 1.895. Now this can simply be interpreted as the ratio of population variance estimated by variance amongst the sample means, which is the numerator, divided by the population variance as estimated by the variance within the sample. And the ratio is simply the difference between the two estimates. So one estimate is 1.89 times the other estimate. The smaller this ratio, the closer the estimates, hence more likely that all samples have been extracted from the same population. The further or bigger this ratio, thus less likely is the likelihood or the probability that all these samples are coming from the same underlying population. That is why we call this test the analysis of variance, that while we are analyzing the variance, we are still testing the underlying means of the different samples. And how do I actually interpret this F value? The F value is can be looked at based on the distribution of the F table, underlying F table. What it essentially tells us is the F value distribution is a one-sided continuous probability distribution. So if I have, so I'm going to go back to the drawing program again and look at, so let me bring in a new sheet over here. What we see of an F table simply is that I plot the F values on the x-axis, and we have a continuous probability distribution. Let me make this an F. Yeah. Right. So the F statistic is going to range from very close to 0 to all the way till infinity, depending on what is the ratio that I get. And based on the F value, if I get an F value of, let's say, F1 over here, the P value or the F value is, we'll compare it against the alpha. So we look at the total area which is in the values beyond F. So I look at the right hand side of the tail, I look at this total area, this gives the P value. So this tells us the probability of an F value coming at this point or more extreme if the null value is true or the null hypothesis is true. The larger the F value, the smaller is the area of the shaded region. The more the F value approaches the origin, so the more is the probability of this coming close to 1. So the P value is nothing but the extremeness of the F value. So the more extreme the F value, the smaller is the P value, or smaller is the probability of null being true. The closer the F ratio towards 0, the more is the shaded region, therefore more likely is the null to be true. So I look at the F value and I figure out that does F lie below alpha or less than alpha. For each degrees of freedom, the F table is slightly different, so we need to actually look at the F table based on the degrees of freedom. But in the previous slide, we've got an F value of 1.895. Let's say 1.895 lies over here. The critical value of F at alpha equal to 0.05 lies over here. So in this case, my F value lies in the acceptance region, so I go with the null hypothesis. In case my F value lies greater than critical value, therefore it lies in the rejection region, I go ahead and reject the null hypothesis. So the F value interpretation is similar to what we get for P value in the t-test as well. I can look at the F value directly on the table, or in most statistical tools the F value will automatically be converted into a P value, and we will be able to interpret it by looking at the P value alone. So One way of doing this quickly is we can do an F test or the ANOVA test on Excel itself. So I'm going to look at this data set we've got over here, and I'm going to generate an Excel result for an ANOVA over here. So let's look at this data set. Let's copy this, go to Excel, paste it over here. In the data analysis tool pack, go to select ANOVA single factor, press OK. Look at the selection range. I'll select this whole. So we've got independent variables, labels in first row, and it is grouped by columns. So each different columns make my different samples and not based on rows. So I let it be as columns. Press OK. So here we have. So we've got three samples: sample A, sample B, sample C. Each sample has got 7 observations each. We've got the average of the three samples separately. We've got the variance of each of the samples separately. So here we get that the between group variance is coming out to be 62. Within group variance is coming out to be 294. The mean between group variance is 31.04. So as we see in the slide, it's 31.05. So you can actually round it off to 2 digits. So it becomes 31.05. Within group is 16.38. So we get 16.38. The F ratio is nothing but within group mean variance divided by between group mean variance. We get an F ratio of 1.89, and it automatically calculates what should be the critical value. The critical value for this data set is 3.55. So as we can see that the F value is much lower than the critical value, therefore it lies in the acceptance region, and the p-value that we get is 0.179. So the p-value is actually higher than alpha at 0.05. So we are going to go with the null hypothesis. So as explained in our previous lectures, the p-value is nothing but the probability of null being true. So in this case, the null being that sample A, sample B, and sample C are coming from the same underlying population, i.e. the means are same, or the difference in the means that we see for these three samples over here. So we see the sample A has got a mean of 7.2, B has got 10.4, C has got 6.42. Prima facie, if I look at this, I see the three samples, they have different means. They can't be the same, they're coming from different populations. But an ANOVA is telling me that this variance that you are seeing is quite likely, it's possible, or 18% chance that it is coming by chance or by a sampling distribution error. So there is no statistical proof to say that these three samples are coming from different populations. They could be coming from the same population itself. So based on an F test, I'm going to go with the null hypothesis, i.e. failure to reject the null. The difference between these three samples is not significant. They could very well be coming from the same underlying population. As you can see, I did it with one test itself. And again, a recap. Why do we call it analysis of variance? Because we are calculating the variance between the groups. Within the groups, we look at the mean variance between the two. We calculate the F ratio. F ratio is nothing but an estimate that how close is my population variance estimate by looking at these two methods. If it is very close to each other, the smaller the F value, the more likely is the sample coming from the same underlying population. The larger the value of F, and if F is greater than critical, I will actually go ahead and say that the underlying populations are very different from the two. How do I generate the F critical? So if I look at the data over here in the data analysis, when I'm doing ANOVA single factor, the alpha is already set at 0.05. I want to change it to, let's say, 0.10. I simply rerun it again. Sorry, this is looking on this one. I want to go to my sheet 1 tab here and run it. Yeah, so I change alpha to 0.10. I press OK. What you will see is the result is the same. I get the same p-value, I get the same f value as before. So if I look at sheet 4 and sheet 5, nothing has changed. It's the same F test which has been performed, but I get different critical values. So if I at 5%, the critical value is 3.55, but if I test it at 10%, the critical value comes down, because if I increase the value of alpha, we all know that the acceptance region goes down. I am more likely to reject. So in this case, alpha has the critical value has come down from 3.55 to 2.62, but my F value is still lower than that. So till the time the alpha goes up to 0.20, my p-value is going to be higher than alpha. So if I test this at 5%, I'm still good to go with the null. If I test it at 10%, I'm still good to go. If I test it at 15%, I'm still good to go. But if the test is at 20%, then I'll reject the null and go with the alternative. So this was, in a nutshell, how do we perform a one-way ANOVA. The procedure to do it on SAS is very simple. So the syntax for SAS and some exercises on ANOVA, we will do that in our next lecture.